Hi there, this is your favorite non-intim math channel, and we have a limit problem. So here in general, if we have something we are adding at the denominator, or it can be at the denominator, we can try using Stolz theorem, which says that so here at the denominator we have n squared, which would go to infinity and it's increasing. So I can say this denominator is just bn, n squared. And for the top part, let's call it Sn, which is equal to, so I'm gonna write it like summation, so we can easily see what is S of n plus 1, okay? Because for this theorem, we need to check if this limit exists, limit as n goes to infinity, that Sn plus 1 minus Sn over Bn plus 1 minus Bn. We know that if this limit exists, it's equal to limit of Sn over Bn, which is our question. So Bn squared is this. I can write Bn plus 1. It's just going to be n plus 1 squared. For Sn, so I'm just going to say it's this thing. And this looks like, so if I say ai, I is going from 1 to n. ai, I would get all of these a values, and I have all of these indices adding up to n plus 1. So I can say this is just n plus 1 minus I. And if we check it, if I put I is equal to 1, this will give me a1 times n. If I put 2, this is correct, okay? So S of n plus 1, so instead of n, I'm going to put n plus 1. So this is going to be I from 1 to n plus 2. Okay, let's write this at the bit more down part. So I have S of n plus 1. So instead of n, I'm just going to put n plus 1. I is going from 1 to n plus 1. ai n plus 2 minus I. So I put n plus 1, so it became n plus 2. And if I open this, so if I put 1, it's going to be a1 times, when I put 1 for I, it's just going to be n plus 1. If I put 2, it's going to be a2. So it's just going to be decreasing by 1 again, a2 times n. So it's going to go like this. Let's write the last two terms. So if I put n here instead of I, it's just going to be a n times 2. And the last term is just going to be when I put n plus 1. So it's going to be plus a n plus 1. And if I put n plus 1 here, it's just going to be 1. If I put n plus 1, yeah, it's just going to be 1. Okay, cool. So now I can calculate Sn plus 1 minus Sn. My cat is destroying me. Sn plus 1 minus Sn. So here, if you notice, I'm going to compare it here and here. I have a1 times n plus 1, and here I have n times. So if I decrease it, if I just subtract it, it's going to be a1. And if I look at here, I have n times a2, here n minus 1 a2. So it's just going to give me a2. And it's going to go like this. And so here I have 2an, here I have 1an, so it's going to give me an. And I have the last term, which here there is no such term, so it's just going to be one more an plus 1. Okay, cool. So I found my Sn plus 1, Sn plus 1 minus Sn, which is equal to limit as n goes to infinity, a1, so it's going increasing by 1, an plus 1, over bn plus 1 minus bn, so n plus squared, n plus 1 squared minus n squared is just going to be 2n plus 1 if you open that. And now I have kind of similar problem, but it's much simpler. I can do this Stolz theorem again. 2n plus 1 is increasing and it's going to infinity. So I'm saying let's call this thing dn, okay, a1 up to an plus 1, and let's call this thing en. It doesn't matter. So I have 2n plus 1. So if I do this thing again, I'm just assuming this limit exists because it obviously exists. Limit as n goes to infinity. So it's going to be dn plus 1 minus dn, which would give me just a loss term, an plus 2. And en plus 1 minus en. So instead of n, I'm going to put n plus 1. So it's going to be 2n plus 3. And if I just subtract them, I will get 2. So in the question, I'm given that limit of n goes to infinity, an is equal to a. So an plus 2 will also go to a because this limit exists, and it's same for any subsequences. An plus 2 is just a subsequence. So therefore, I can say this is just limit n goes to infinity an plus 2 over limit of 2, which is just going to give me a over 2. And this is our answer.